escape speed. This is the speed needed to leave a planet. So here's our planet, and let's say that that planet has a mass m. Now maybe we have a rocket or something, and we want that rocket to be able to make it infinitely far away from our planet. So I'm going to put infinity way out there, and then we're going to move this rocket from the surface of the planet here all the way out to infinity. So there's an energy needed to launch this rocket. So let's draw an energy bar chart. So we have the planet and the rocket as our system. And now I'm going to draw my LOL, but my L's are actually going to not look like L's anymore, but sideways T's maybe. But this is because we can have negative energy stored in our planet rocket system. Now initially there's some energy, but when we get far, far away, when r is equal to infinity, the gravitational energy is 0. Now remember, this doesn't mean nothing. And let's say we're just going to make it out here to infinity, and when you just make it somewhere, like just coasting up a hill, the maximum position, the velocity would be 0, so then our kinetic energy is 0. So over here on the right side, we have 0 total energy. Now initially, because the energy stored between the planet and the rocket is negative, it is drawn in the negative quadrant here. So the negative GMM over R is represented by these blocks below the 0 axis. Now in order to leave the planet, we're going to have some energy, but we also see that mathematically we have to add these up to get 0. So that means that we have to have some sort of positive blocks, chunks of energy, and so that's our kinetic energy needed to leave the planet. And so when I add a negative and a positive, I can get 0. So now let's write our energy equation for this system. So we have negative GMM over R plus 1/2 mv squared. So this will be the velocity we leave the planet with, and that's going to equal 0. So let's do a little algebra. GMM over R equals 1/2 mv squared. Again, the little m is the mass of the rocket. I can actually divide by the mass of the rocket on both sides, and we get that our final velocity is the square root of 2gm over r. And this is our escape speed. So how fast, at minimum, do we need to be moving in order to escape the planet? And this r is the radius of the planet.